it is going to YouTube. So right now, everything that I do on the projector, as well as my voice, are being streamed to YouTube. You can actually watch it with about a 20-second delay on YouTube. And I can see what the next question is going to be. Where on YouTube do you find my lectures, right? Seems to make sense. So let's go ahead and start up my Chrome here. Takes a little bit of time. This is a really old computer. And go to YouTube. So once you go to YouTube, you can go directly to my channel. The name of my channel is Some Profs. You might want to write it down because unless you write this down, you cannot rely on the recording when you don't know where to find the recording. So you got to write down the channel name, which is just Some Profs. And once you get there, you can look at my videos. So right here, you can click on videos as a tab. And that will show you pretty much everything that I have recorded in the past. I have about 2,000 something video clips, dating back maybe by 5 years or so. Okay, if you guys want to dig up, how I taught this class 5 years ago, feel free. Okay, it may or may not be relevant to how I teach it now. So this one shows live now, which means it is the one that that is currently being streamed, and you can definitely click it too, just for curiosity's sake. Live now, which means it is the one that is currently being streamed, and you can definitely click it too, just for curiosity's sake. Live now, which means it is the one that has been. So as you can see, it can be amusing. Okay, if we were to do this in class. Just for curiosity. So are there any questions about how to find recordings of this class? So after the class, when I have time, I'll go back and change the title. So it will read 2018-08-27, which is August 27th. And then the name of the class is cisp310. Okay? So I will do the same thing with my Tuesday, Thursday class. So in order to find which one is yours, you just need to look up your calendar, find out what days are Mondays and Wednesdays, and those are the ones that I record for this specific class. Now, in the past, I also have students who watch the Tuesday, Thursday class because sometimes I present the material differently. I use different sample programs and so on and so forth. So it can be beneficial to watch the video of the other class. All right. So I put everything on Canvas. So you should have an account already set up on Canvas unless you're trying to add to this class, which we can do a little bit later. So if you click on this class, then you will start to see everything is already in place. The homework is not visible yet, except for the one that I want you guys to do during lab time today. So we do have lab activities that we are supposed to do in the lab. So that 1 hour and a half is not optional. Okay. Now, when you're done with the lab activities, yep, you can go ahead and take off or have lunch or whatever. But we do have scheduled activities in the lab. All right. So let me go to this portion first. So this is syllabus presentation, which is a pre-recorded presentation of the syllabus or the common part of the syllabus. So you're supposed to go watch that. Okay, it's only about half an hour that talks about classroom policies, late policies, what else? Academic honesty type of issues, and other things too. The content of this is actually also here. So if you click on this link here, it will bring you to a web page. You can either read the PDF portion, print it out and include it in your binder, or you can just read the HTML portion, in case you need to go back and refer to it. So the only portion that is not covered in the video is this part here. So this part is completely dependent on which section you're taking. So in this case, you're taking the Monday, Wednesday section. So as you can see, there's no scroll bar, so that's good. So as you can see, this is very specific to this class. We are meeting on Mondays and Wednesdays from 10:30 to 11:50 and so on and so forth. This is the information that you're supposed to get for every single class. It's called the learning objectives. In other words, I'm spelling out, at the end of this class, what you should be able to do. So write simple assembly language program segments, and so on and so forth. So we'll refer back to this list, as we go along in this class, just to make sure that we cover every single one of these learning objectives. The last portion that is specific to this class is a schedule. It is a tentative schedule, and I tend to go kind of off of the schedule. So don't be alarmed if I do not follow this particular order. Okay? And that's about it for this portion. So are there any questions at this point? No questions? All right. So if there are no questions, I'm going to let you guys watch the syllabus presentation, which is nothing more than another YouTube thing, so that I can talk about the portion that is common to all of my classes. So unless anyone has a specific issue about that, I would prefer to kind of jump into the content of this class. So are there any questions, any concerns before we get into the content of this class? Okay, nothing? Cool. All right. Like that. But definitely use your time to watch the syllabus presentation. Okay, it is kind of important. All right. So what we're doing is we're starting with physical states, truth, what is Boolean, numbers, how we represent values, and also computers. Okay. So when you look at the content from here all the way to the end, the objective, if I want to summarize what this class should be able to allow you to do, is at the end of this class, you can look at a C++ program, and then you get an X-ray vision of what is underneath that program. Okay, it turns into assembly language code, which turns into binary machine code, which then turns into microcode that your processor can execute, which then turns into instructions to the registers, multiplexers, demultiplexers, RAM, ROM, and so on and so forth. And you start to see, at the very lowest level, what is going on inside your computer. So that's the overall objective of this class. Any questions? No questions? All right. So if there are no questions, I'm going to start with this. Obviously, no one has time to read this ahead of time. Some of you might. I mean, I get you guys into this class maybe yesterday, and some of you might have been curious and go just click on the links and check it out. But that's okay. We're going to start with this. And just like most of my notes, it is written in a way so that you can either click on the PDF or you can click on the HTML. So this gives you the ability to print out the PDF, if you want to keep a copy in your binder, or you can just kind of read it online. Even on a cell phone, it shows fairly well because I don't do anything fancy with HTML. So it's really plain and simple HTML for the most part. So you don't really have to pay attention to the module number. It's really just a unique ID, so I can identify one module from another module. And this is pretty much how I present material in this class. There's the HTML document or PDF document, depending on which one you're reading. And I just go over that in class. So it really helps if you have time ahead of class to read this material. Get your questions. If there's a particular portion that you don't understand, jot down your question, ask those questions in class. The first class obviously is exception to that rule. Any questions so far about how to find the reading material and what you're supposed to do with the reading material? Read it, of course, right? All right. So is this level of zoom okay, or do you guys want to zoom in a little bit more? It's all right for now? Okay. So if you need to zoom in more, just let me know. All right. So this section has to do with physical devices, which talks about what kind of technology people use in order to implement computers. Okay? In other words, if you kind of look into a computer, what kind of devices can you expect to find over the history of all the different computers? So 2.1.1 talks about electromechanical devices. Now, we still have a lot of electromechanical devices that can be used to implement the computers. The simplest one is called a relay. How many people know what a relay is? Electrical relay, okay? So a relay is a device where you can use a current to turn on and turn off a switch, which in return is going to complete or discontinue the circuit of another current path. Okay, so that's one example of an electromechanical device. And if you read the notes here, the most commonly used electromechanical device to implement computers were not relays. They were basically a motor that has a rotor. The rotor itself has multiple contact points, so depending on the position of the rotor, which is controlled by a motor, or otherwise, other mechanisms to turn it, then the rotor can connect different portions of the computer together by electrical pathways. All right? Has anyone watched the Imitation Game? Okay, some people have. And how many people have not watched that movie? All right, so if you have time, during your spare time, it's a movie that I highly recommend because it really kind of explains, the beginning of computer science, the people who were super influential to computer science that we have at this point. So that occurred in the late 40s, 1940s. And the computer science or the theories that Alan Turing came up with during that time, it's still in place today. So even though computers have gotten a lot faster, the basic theory of how computers operate have not changed at all over these 50 years. So that's something that is worth mentioning. Of course, you can also kind of look up pictures because I know pictures really help. So if you look up Alan Turing, Wikipedia has a pretty good page on him, but what we are more interested in are the machines that he helped invented. So if you look up the machine that he invented, I think there's a name here. So the Enigma encryption machine is a device for encrypting. It looks like a typewriter. So if you look it up, Enigma encryption or encoder. This is a picture of that particular device. If I click on this, it shows a bigger picture. So as you can see, it looks kind of like a typewriter. Okay, it has got some light bulbs here, and then a typewriter keyboard here, and then there are these discs or wheels. Okay, and by combining these things in different order, when someone types, these things will start to rotate. Well, actually, they don't rotate, but it will transmute. So whatever you type is going to be translated, it will be mapped to different characters. And then that's all done before the message is broadcasted by radio wave. So that means, when the Germans were doing this, the transmission itself is received by the Allied, the enemy, army. But because they cannot decrypt it, they don't know exactly how these disks were configured, they could not know the actual message. So that's the general idea. So in a war, don't you think it would be kind of helpful if you are fighting an enemy who's using encrypted messages? Don't you think it will be beneficial if you can decrypt it, so that which invasion is going to occur when, and the planning of the other side? So that's what the Brits were trying to do. They were trying to crack this encryption. They were able to do it by hand when there were relatively few of these disks. But when they added, I think, the fourth or the fifth one, it became intractable if you were to do it by hand. And that's why they needed a machine to do it. Okay? The machine that they used to do it, okay, let me go back to my module here. So the machine they built to do this was called the electromechanical, and the name of the machine is called BOMB, B-O-M-B-E. And it was able to decrypt messages actually faster than the Germans do it by manually. So that's some accomplishment. And you can look up the this name here and look up some pictures, because it's always kind of helpful if you can get an idea of what it looks like. So here's one, and let me see if I can get a bigger picture. That's about the biggest I can find, but you can definitely look up other YouTubes or pictures of this. So you can see how there's a lot of these disks. They're all connected to routers, and they're electromechanically actuated. So basically what these things are doing is they're testing combinations to find out which combination unlocks the message. Okay? So these are all electromechanical devices. What do you think is one of the attributes of an electromechanical device that is not so good? There are a few. There are reasons why we don't have electromechanical computers anymore. What do you think is going to happen if my Fitbit was electromechanical? Yep. It'd be huge, exactly. I would probably think that my Fitbit has more computation power than one of those computers, easily, by a few orders of magnitude at least. Okay, that's one, okay, size-wise. Two, energy consumption. Do you think I can charge my Fitbit once every 5 days if it were electromechanical? No way. Okay, it's going to consume a huge amount of electricity or energy to do any type of computation. But this was what was available at the end of World War II, or close to the end of World War II. So the computer scientists and engineers, they don't have a choice. This is all the pieces they got, and they have to work with these. Is that okay? All right. So after the end of World War II, people started to use, well, actually, even at the end of World War II, some computers were using vacuum tubes already. Does anyone know what a vacuum tube looks like? Okay, how would you describe it if you were to just look at a vacuum tube and you have to summarize what it looks like in one sentence? What do you think it looks like? Yep, exactly. It looks kind of like a light bulb. When it operates, it has a kind of very low intensity glow to it. And the shape, because it's made out of glass, it looks kind of like a light bulb, except it looks kind of funny because there are some wires and meshes in the inside of that tube. So if you click on these links here, it will bring you to the Wikipedia page that shows you a picture of what a vacuum tube looks like. So these are various vacuum tubes, and you can see how all of these are made out of glass, multiple contacts to connect to a circuit board, and then inside they have a heating element, and the heating element is what makes it glow. Okay, usually it's kind of low glow, it doesn't shine really brightly. And then almost every single one of these have some kind of plates outside of the innermost, the glowing portion, the portion that heats up. So I'm not going to ask you guys to explain how they operate, okay? But the basic principle of vacuum tubes is the heating element is going to heat up the metal, and when metal is heated up, the electrons are basically free to move around, including going out of the surface. So what they do is the plate around it can be charged. So if it is charged, then electrons can actually jump from what we call the cathode to the anode. The cathode is the negatively charged portion, and then the anode is the positively charged portion. And the name of the device is called vacuum tube because inside is not complete vacuum, but it is pretty close to complete vacuum, and that's how electrons can travel from the surface of a heated metallic surface that is negatively charged to another surface that is positively charged. Is that okay? Sort of? Yep. Well, it is a switch, basically. It's a valve, okay? And that's how people implement computers when these devices were available. Yeah, basically, the idea of a component in a computer is it is a valve. Okay, it is some sort of device that can be used to connect or disconnect the continuation of another path. So as long as the controlling mechanism and what it is controlling are of the same nature, then it will work. So you can use water if you want to. You can use electricity if you want to. Yep, go ahead. Because if the element is not heated, electrons do not want to jump. They don't want to leave the surface. But if it's heated, then it's energetic. So that means that the electrons are much more willing to get out of the negatively charged surface to jump to the positively charged plate. It's a heating element, so I would assume it's tungsten based, because that can last a little bit longer than most other types of metal. So it's a light bulb filament. Its only job is to heat it up to a point where electrons are ready to jump. All right. So we are not going to be talking about the actual physics behind how vacuum tubes work, but it might be worthwhile to kind of read through this a little bit just to get an idea, okay, just for your information of how they work. Now this part here is kind of important. So a triode, which is the most basic and useful component to make a computer out of vacuum tubes, is a non-mechanical and non-hydraulic valve. Now because it's not mechanical, it can be a lot faster than an electromechanical device. An electromechanical device like a relay takes a bit of time. So from the time you apply a current to the time that the actual mechanical switch is actuated, you're talking about tens of milliseconds at least. These can operate a lot faster because there are no moving components. Okay, so it's good. Okay, this is one big step up from electromechanical devices. But the problem with these things is they are bulky, they run hot. Okay, they run hot because of the very principle that makes it work. The heating element is needed in order for vacuum tubes to work. And as a result, they consume a lot of energy. And that's why, when you use these as basic components to make computers, those computers tend to be physically large. Okay, so we are still talking about physically pretty big computers consuming, a huge amount of current or energy by today's standard. But they were much faster than the electromechanical devices already. So this is kind of like a second generation of modern day computers. Are there any questions about this part? An example of a computer that is implemented mostly by vacuum tubes is this guy here. I would say Lorenz computer. It is also a computer used to decode or decipher encrypted messages, but it's not to counter the Enigma machine. It is used to decipher. Oh, okay, I got it the opposite way. The computer to do the deciphering is called the Colossus. The encryption machine is called the Lorenz cipher. So I got it reversed. Okay. The reason why the Colossus is made out of vacuum tubes but not electromechanical devices is because the Lorenz cipher is far more sophisticated than the Enigma machine. So that's why you need the computer to operate faster. Okay. But the other thing about the Lorenz cipher is the cipher itself, or the encryption machine, is also pretty big and bulky. So that means it cannot be deployed into the field with every single branch of the military. It is usually only between established offices. So it cannot really be used in the field. All right. So this is all pretty cool. Now we are moving on to things that we are still using to date, transistors. So the name transistor, why do you think it's called a transistor? What type of electrical device has a name that is very close to a transistor? Resistor. Okay, very good. So what does a resistor do? As the name implies. Resist. Yep, it slows down, okay? It slows down and it resists, right? So what do you think a transistor is going to do? It's kind of like a resistor when we want it to be a resistor. Other times it can be a non-resistor, which means it lets your current through just fine. Other times we can say, okay, let's turn that thing off. Okay, it becomes a device that has close to infinity or close to, it's a huge amount of resistance. So current doesn't want to go through anymore. So it's a switch, basically. A transistor is nothing from our logical perspective. It's nothing more than a switch, okay? You apply a voltage here, it turns on, and you remove that voltage, it turns off, okay? Something along that line. I'll explain in more details later. And the basic principle of a transistor or any semiconductor device that we are using today is based on the concept of a p-n junction. P stands for positive, N actually stands for negative. This is how we can dope semiconductor material. So you can DOP, dope, is the name where you turn a semiconductor material into a non-semiconductor material. Okay, silicon is a semiconductor material. What do you see in this classroom that has a lot of silicon? Well, we have blinds, hiding those things from view, but glass. Okay, glass has a lot of silicon in it. So the next question is, do you think glass is a conductor? Can you conduct electricity, from one end of the window to the other end? I'm not talking about the frame. I'm talking about the actual pane, the glass itself. Glass itself is not a conductor. Okay? So if we use silicon to implement computers and we say those things are transistors, they have to conduct current. Okay? So how do we make something that does not conduct current into something that does conduct current? We dope it. Okay, that's the actual technical term. We dope the silicon material into something that is conductive. How many people here have taken basic chemistry, like college level chemistry? Okay, so if you look at silicon, okay, how many electrons are on the outermost orbit? 4. Okay, so when you make a silicon crystal, what happens is one silicon connects to 4 other silicon, and then each of those silicon connects to 4 silicon, and so on and so forth. So you don't have any free electrons floating around to conduct electricity. That's why it's not conducting. So what happens is, to turn it into a conductor, is we introduce phosphorus or some other material. So that phosphorus has 5 outermost electrons. So if you put a very small amount of phosphorus into silicon as it cures, okay, the phosphorus is forced into the crystalline structure, okay? But there's a problem because phosphorus has 5 outermost electrons. The structure is going to use up 4. Now you have 1 electron that is just kind of floating around. And that is why it can conduct, because now we have free electrons that is free to move around the material. So it can go from one end to the other end. And that's why an impure piece of silicon with phosphorus in it is actually a conductor. So I'm not going to explain how p-n junction works in general. For those of you who are curious, you're more than welcome to look it up. And if electrical engineering is your major, you have to understand that part. It's called device physics. But it's really cool because of the very basic physics of a p-n junction, now we have transistors. Transistors, just like vacuum tubes, is basically used as a switch. Okay, so you can apply different voltages at a certain part, and it can control the conductance through the other part. Okay. So we'll get back to this one later. Regardless of the device that we are talking about, we just need to understand the physical states. Now, with a valve, okay, what do you think is the simplest way to look at the state of a valve? Like a faucet. Is it on or off, right? If the valve is quote-unquote on, it is letting things to flow through it. If a valve is off, it's cutting off that flow. Okay, that's a very simplistic view of the state of a particular valve device. It's either on or off. On or off. How many states are we talking about? 2. What kind of type in CISP360, also theoretically speaking, only has 2 states? A Boolean, okay? Something that can either be true or false. Is that okay so far? So that means, we can kind of look at a valve the same way. Okay, instead of calling it on, we can say, oh, it's representing the value of true. Instead of looking at it as off, we can say it's representing the state of false. So we can map what you already understand in Boolean algebra or Boolean variable types to devices, to physical devices, valves. Is that okay? Cool? All right. So that's what this paragraph is really talking about, is how do we map concepts that we have learned in programming, in mathematics, into actual physical devices. It's just on and off. Okay? Are we allowing flow through? Yes. Okay? So we can look at that state as quote-unquote true. Or if you choose, you can also look at it as 1. Something that's off, you can look at it as 0. Is that okay? All right, cool. So that kind of talks about this part too. Basically, we are really just mapping truth values to the state to the 2 states of a transistor. So now the question is, can we map the state of true to a valve that is off? So off means true and on means false. Yeah, you can do that. The mapping is somewhat arbitrary. Okay, if true is one state, then false has to be the other state. Okay. So at this point, we are looking into transistors just a little bit more. So this is actually where the kind of tedious but technical content of this class starts. All of the other stuff is really just to lead to this point. So there are 2 types of transistors. There's a P-type transistor, there's the N-type transistor. It has to do with the material of the substrate. We don't have to understand that, okay? But if you're an electrical engineer, that becomes really important. So we'll talk about the N-type transistor first, or an N transistor. This is the symbol of an N transistor. Okay, it's got 3 terminals, 1, 2, and 3 terminals. It has got a symbol that looks kind of funky. So there's 1 terminal coming here. Okay, let me use a mouse pointer so that is also captured. So it's got 3 terminals. We have 1 terminal here that goes to a particular plate. Then it is disconnected from the rest of that device. And then we have the other 2 terminals, this one here and also this one here, that is somehow connected. Okay, you can see there's actually some kind of physical connection between these 2. And then there's a little arrow here that seems to indicate some kind of flow. Okay, and that's an N transistor. So with an N transistor, the characteristic of an N transistor is if this terminal here, once again, let me go back and use my mouse pointer. So with an N transistor, if this end is experiencing a positive voltage, the device allows flow. It's turned on. Okay. On the other hand, if what the mouse pointer is pointing to has 0 volt, then the device is off. It does not allow flow through it. Is that okay? High voltage means the device is on. Low voltage means the device is off. So what I'm pointing at right now, that terminal is known as the gate, okay? Or simplified using G, to represent the gate. And then the other 2 terminals, one is called the drain, and the other one is called the source. You always go from the source to the drain. In other words, the arrow here, it's always pointing from source to drain. So now we have the 3 symbols. We have the terminal pointing to the left-hand side being the gate, or G. The terminal that is to the south is called the source, or S. And then the terminal to the north called the drain, or D. Is that okay? All right. And once again, the characteristic is if the gate has a high voltage, the device allows flow to go from source, which is south, to the drain, which is north. But that flow is, because it's an N transistor, is going from a negative voltage source to a less negative drain. So it's a negative type of current that's going this way. Yep.
So it's not negative and positive, it's negative and less negative?
Right. Because you're just looking at a voltage differential that allows the flow of electrons. Okay. So that's one device, and we have the other one. The other one is called a P transistor. And let me display both at the same time so you can compare and contrast the two types of transistors. So what do they do? They do look very similar with some really minor differences. So how can you describe the difference between the two transistors? Not counting the mirror image effect. So what is the only difference between the two transistors? There's a little bubble, right? So there's a little bit of bubble here with a P transistor that is lacking in an N transistor. A bubble in these schematics usually means negation, which means the opposite. Okay, so using that understanding, that means a P transistor behaves kind of the opposite of an N transistor. When the gate has a negative or has a low voltage, the device is on. It allows flow. When the gate has a high voltage, it turns off the device. Is that okay? So the bubble is your big clue of how to interpret what the gate is going to do. So in this case, it's negated, which means if the voltage at the gate is positive or high, the device is off. If it's 0, the device is on. The direction, this arrow here, is still pointing from source, which now is the north, to the drain, which now is the south. But that flow of charge is not about negative charge anymore. This one is about positive charge. Okay, so we are allowing positive charge from the north to flow through the device to the south. Are we still doing okay so far? Okay. All right, so now we want to look at a circuitry like that. Okay, so there are a few things before I can explain what it does. We have to be able to understand what the circuitry is representing. The little squares to the left-hand side and the bubble to the right-hand side, those are pins, P-I-N, pins. Input pins are squares, and the only output pin is a circle, is a bubble. Okay? So the input pin is what you can specify. Oh, I want X to have a high voltage. I want Y to have 0 volt. You get to control the state of the input pins. The output pin, on the other hand, is the actual output of the system, which means after it does what it's supposed to do in between, the output pin can be high or low. Is that okay? You can kind of look at this as a function, okay, in C and C++. X, Y are your parameters, and the bubble is your return value. Is that okay? So in between, we have 4 transistors. The transistors in traditional nomenclature, they use a Q to represent transistors, R to represent resistors in a circuit. So we got Q1 and Q2 being one type of transistor. We got Q3 and Q4 being the other type of transistors. What is the type of Q1 and Q2? They're of the same type, but which type is it? Is it N or P? They are of the P type because they got a little bubble. Q3 and Q4 are N types. Okay? And you can also see that the direction of the little arrow is different because this symbol, the little triangle at the very top part of the circuit, means positive voltage. It's called the supply voltage. And then this little symbol at the very end or the south end of the entire circuit is called the ground symbol. Ground symbol basically means 0 volts. And then the other symbol means some kind of positive voltage. We don't know exactly what is the actual voltage because that depends on what type of transistor we are talking about, but we know it is positive. Are we doing okay so far with this? Okay, so let me just kind of repeat what we have already said so far. These two are input pins. You can specify the voltage of those pins. This is what we call a supply voltage. It is some kind of positive voltage. This is called ground, which is basically 0 volt. This is the output pin. Okay, after it does quote unquote computation, the output pin will become either high or low. Are we doing okay so far? Okay. So with Q1 and Q2, because they are P transistors, they allow positive charge to go from the source to the drain. Okay. Q3 and Q4 are N transistors. They allow negative charge to go from source to drain. That's why the arrows are opposite in direction, because the N transistors are basically connected to 0 volt as the negative charge or the source of negative charge, and then Q1 and Q2 have their sources connected to the positive voltage as the source of positive charge. Is that okay? More or less? Okay. So now we want to kind of think about several scenarios. So I'll keep the picture here, and I'm going to use mouse pad to kind of explain things on the side. So I want to ask you, what do you think this is going to happen? If X is low and Y is low, 0 is the same as ground, or negative voltage. If X and Y are both zeros, okay, I want to know the states of each and every transistor before I can figure out what the output is going to be. Okay. So can someone tell me whether the states of Q1? Is Q1 on, meaning it's connecting, or is Q1 off, meaning it is not connecting? Q1 is a P transistor, is on, okay? Because a P transistor turns on when the gate has 0 volt. Okay, so we'll just write it down. Okay, we'll annotate this. Q1 is on. It connects. Okay. Q2 is the same way because Q1 connects to X, Q2 connects to Y. So Q2 is also on. It also connects. What about Q3? Q3 connects to X, right? X is a 0 or the low voltage, but Q3 is not a P transistor. Q3 is an N transistor. So when the gate of an N transistor is a 0 or low voltage, is the transistor turning on or off? It's off. Very good. Okay, so Q3 is off. It disconnects. And then Q4 is in the same boat. It also disconnects. So at this point, it is as if Q1 and Q2 are just straight lines, okay? Because they're just connecting whatever they're connecting to, which is this node here, to the positive voltage. But at the same time, Q3 and Q4 are as if they're not even there. So just kind of imagine the Q3 is not even there, Q4 is not even there. That circuit is not complete. There's no path to connect the output pin to ground. But there are two paths to connect the output pin to the positive voltage. Is that okay? So what is the output of this circuit when both X and Y are zeros? It's positive, but we can also interpret it as 1. Okay, very good. So output is 1. All right, so let me, go ahead. Because Q1 and Q2 are connecting, so it is as if we just have a wire connecting these two ends and also connecting these two ends. But Q3 and Q4 are off. They're disconnecting, so it is as if the device is taken out completely. So now when you trace from the output pin, it got two directions to go. But this path here, going south, it doesn't connect to anything, right? But when you trace the path to the north, it can go through this, and both of these paths are connecting. So now you have a really good connection to the positive voltage. And that's why the output pin is going to have a positive voltage.
Let's say like one of them was positive and the other one was
one is positive and one is negative. You mean between Q1 and Q2? Well, we'll work with that scenario next. How about that? So for now, we just have to be convinced that the output pin has a high voltage when both X and Y are low voltage. Yep. Say that one more time.
Like we want to go from the output, right? Yeah, the output, like because you're saying if you want to find out if it connects or disconnects, we have to go like how should I say this?
So you look at each device.
Yeah.
So you look at Q1 on its own, and you say, okay, how is the gate of Q1 connected?
Yeah.
It's connected to X. X is 0. So that means the gate of Q1 is 0. But because it's a P transistor, when the gate is 0, the device is quote unquote on. It allows flow. So that means these two are now connected. So we do the same analysis for all 4 transistors. And that's why we come up with this table here. But once we have this table, we know that we can trace from the output pin and goes, oh, okay, this is already disconnected. There's no way for me to connect here. But if we go the other way, oh, this is connected. But this is also connected. So I got a really good connection to the positive supply voltage. So are we okay so far with this analysis? Okay. And before I forget, which I tend to, I'm going to pass the row sheet. And this is also why you want to read the syllabus, because 3 unexcused absences is considered excessive, which means I can drop people after the 3rd absence, unexcused absence. And the only excused absences are due to sickness of the student. Okay, so that's kind of important. Just want to kind of let you guys know about that first. All right, so let's play out another scenario. X is 1, Y is 0. Okay, so this is a slightly different scenario. And let's try to figure out what is the state of Q1 first. What do you think is the state of Q1? Is Q1 on or off? It's off because the gate of Q1 connects to X, and X is high at this point. But because it's a P transistor, when the gate is high, the device is off. Okay. Which also means it disconnects. Okay. It is as if the transistor is not even here. It is not going to connect anything. All right. So let's look at Q2. Q2 is also a P transistor. The input connects to Y, which is a 0. But because it's a P transistor, when the gate is a 0, the device is on. Okay, so that means it connects. Okay, so this is on. It connects. And then Q3. What about Q3? Q3 connects to. Now this is all. I forgot to explain this part. Even though the gate of Q3 seems to connect to Y, it is not. Okay, this is what we call a flyover connection. If you don't see a little dot or bubble, the connection is not there. So Q3, the gate of Q3 does not connect to Y, it only connects to X. Q3 is an N transistor, X is high, so when the gate of an N transistor is high, is the device on or off? The device is on. Okay, so if the device is on, it connects. Okay. And then Q4 is, what do you think? Q4 is off because it connects to Y. Y is low voltage, so that means it disconnects. All right. And we want to figure out what is the output in this case. So let's try to analyze that. This is our output pin, and we'll track down which way it connects to. Hopefully, it only connects to one end, because if it connects to both ends, it's called a crowbar. And a crowbar means you have a very low resistance path from the supply voltage to the ground. Why do you think that's a bad thing, if it can happen? It's the same thing as sticking a thick copper wire into the 2 prongs of an outlet. Don't do it, but I'm just going to hypothetically ask, what do you think is going to happen? You just stick a thick copper wire into the two terminals of a wall outlet. It's a short, and what's going to happen? Don't do it, because nothing good can come out of that. Okay, so it depends on whether you have safety features, right? If you have the proper fuse boxes or the jumper boxes, that fuse is going to blow, or it's going to the jumper is going to kick, so it will disconnect because it's going to exceed the 20 amp, the 30 amp, or whatever that jumper or that the fuse is rated at. What if it's not connected through a fuse to the supply? Then it get very hot, and it will melt itself until it disconnects. Or the house is on fire or something along that line. Okay, so we don't want crowbars. Okay, every time you have a low resistant path from a source of voltage to 0 volts, that's not a good thing. Okay, we don't want it. We don't want that to happen. But let's see if this is going to be one of those situations. So we start with the output pin. We go like, well, let's explore the south path first. Okay, so we go south. If we go south, we go like, oh, Q3 is on. Okay, so the output pin takes a left turn, goes through Q3 because it's on, and then when it hits Q4, guess what? Q4 is off. It disconnects. After all, we could not complete the path to ground. So it is disconnected from ground. Well, let's see if we can connect to the power, to the positive voltage source. Okay, so once again, we start with the output pin. We go here, we take a right turn this time. So after we make a right turn, there are two paths to go. Okay, we'll first explore the left path first. So the left path goes to Q3. We look at this picture. Q3 is on. Good. Okay, so we go through Q1. Okay, I misspoke. It goes through. It connects to Q1, but Q1 is off. It's disconnected. So the left path here is disconnected. Doesn't connect to anything. Cool. We follow the right path then. So the right path will take it to Q2. According to this, Q2 is on. So it will go through Q2 because it's connecting to the positive voltage source. So we do have one path connecting the output pin through Q2 to the positive voltage. So what do you think is going to be the state of the output pin? It's a 1 or high voltage, okay? Positive voltage. Very good. Okay, the next one is going to be an easy one. We just flip the states of X and Y compared to the previous one. So what do you think is going to happen to Q1? Q1's on, it connects. Q2, what do you think? Q1's off, it disconnects. Q3 is off, because we are just flipping all the states compared to the previous one. So Q4 is on, it connects. What do you think is the output? It's going to be a 1, because in this case, even though this transistor is connecting, this one is not. So we can't even get past Q3 for Q4 to even matter. Okay? So there's no path to ground. But on the other side, we got Q1 being on, so we have one complete path from the output pin through Q1 to the supply voltage. Well, all we need is at least one path. It connects, right? So that's why the output pin is still going to have a value of 1, high voltage. How many more? Yeah, go ahead.
So if the path changes and goes to the ground, then the 1 changes to 0. Let's say Q3 and Q4 are the only ones that are on.
Mm-hmm.
What would that figure out to do?
Well, let's work it out. Because we haven't seen that one yet. Okay, so we have X being 1 and Y being 1 this time. Okay. So if X and Y are both 1s, both of our P transistors will be off, right? Because with the P transistor, when the gate experiences high voltage, the device is off. And both Q1 and Q2 are P transistors, so they're both off. Q2 in the same boat. It also disconnects. Q3 is on because it's an AND transistor. When the voltage of the gate of an AND transistor is high, it is on, and therefore it connects. Q4 is the same way. All right, so now what is the output? Let me fill this one in first, and we'll figure out this one now. What do you think is going to be the output? It's going to be a 0, because Q3 and Q4 are both on, which means they're both connecting. So now starting with the output pin, you take a left turn, Q3 is connecting, Q4 is also connecting, we can actually get to ground. What about the other path? You start with the output pin, this time you make a right turn. After the right turn, you take a left turn. Sorry, Q1 is disconnecting. This path, we cannot go through this path. After you make a left turn, let's try another, after you make a right turn, let's try another right turn. So this time we try to get through Q2, but guess what? Q2 is also disconnected. So we don't have a single path to connect to the positive supply voltage. So that means X1, or excuse me, the output pin is only connecting to ground, but not the positive voltage. And that's why the output is a 0. Okay. All right. So are there any questions about these 4 scenarios of how this particular circuit can behave when X and Y can either be high or low voltage, 0 or 1? Any questions about this? No questions? Okay. So if there are no questions about this, the next thing I'll do is I'll turn this into a table. I will basically eliminate all the details. So I don't really care about Q1, Q2, Q3, or Q4. I only want to know what is X, what is Y, and what is the output. In other words, I'm looking at this as a function. I only care about what kind of parameter values will give me what kind of return value. Okay, I don't care about the implementation anymore. So we'll look at the truth table. So X, Y are the inputs, and this is our output. 0, 0, 0, 1, 1, 0, and we got 1, 1. All right, so we'll take a look at this one. X, Y both being zeros, the output is a 1. I'm just copying from what we had earlier. This is also a 1. This is also a 1. And this is the only one that is a 0. Cool. It looks like a Boolean function to me, a Boolean operator. But does it map to any Boolean operator, single Boolean operator in C and C++ that you know of? It looks like one of them, but not exactly the same, right? Well, I would say it looks like 2 of them, but it's not the same. In a way, it looks like an OR, right? So because if you look at OR, we got 3 ones as the output and 1 0 as the output. But it's not quite an OR, because with OR, it means if at least one input is a 1, the output is a 1. That's not what we're seeing here. It also looks like an AND, because as long as I have at least one input being a 0, the output is one particular state. The only time the output is the other state is when both inputs are 1s. That looks like an AND, except it's opposite to an AND, a conjunction. Okay? It is called, we cannot do this with a single operator, but we can do this with 2 C++ operators. We need a negation after a conjunction, after an AND. Okay? So I will let you guys work this out. Okay, so here we have the negation, which is exclamation point, not the tilde symbol. And then we got X and Y here. So work this out. Okay, I'm not going to do it, but I am fairly convinced that this is the case. Okay, we have X and Y, take the whole thing and negate it. This column should look exactly the same as the output of that little circuit. Is everybody convinced that this math should work out, just based on the explanation a little bit earlier? Yes? Woohoo! We got a NAND gate, N-A-N-D, the first N stands for the first negation. It's a NAND gate, okay? I call this a NAND 2 gate because it has 2 inputs, okay? This is a simple device. You can actually go buy transistors, arrange it this way, and you end up with a NAND gate. I call this monumental because now we have just mapped from physical devices for transistors, right, into a Boolean operator that is really odd, that we have never used before. It's called a NAND gate. But nonetheless, it can be translated into operators that you already know in CISP360. Are we good so far? Okay. So now the next question is, who uses a NAND gate? I mean, we know OR, we know AND, we know NOT, but we don't know any NAND gate. That seems pretty odd to me. Well, the first question is, if I use a NAND gate, can I implement all of the other logical operators that we are familiar with, which is the negation, NOT, conjunction, and disjunction, OR? Can we use something awkward like this to do stuff that we are familiar with? What do you think? Yes, we can. The NAND 2 gate turns out to be one of those universal things where you can use a NAND 2 gate to implement, well, not single one, but you can use NAND 2 gates to implement everything else. It is that cool. So the rest of this slide, okay, just kind of talks about the scenarios. Okay, look at these things. We just basically have connections, solid connections versus no connections. So this is explaining things that we have just explained using the table. But this is the part where we can be convinced that starting with a NAND gate, we can do everything else. In mathematics, this is negation. The little cliff symbol is negation, which you know as the exclamation point symbol in C++. This little up arrow thing is representing NAND, okay, N-A-N-D. So I'm going to claim that the negation of x is x NAND x. Does that make sense? What if you're not convinced? What are you going to do? Make a truth table. Exactly. So make a truth table, and you have x as an independent variable, negation of x being one column, and then x NAND x being another column. Work it out and see if the columns of negation of x is going to have exactly the same values as x NAND x. If they do have the same values, then the two operations are identical. They give you exactly the same result. Okay? So this one is kind of trivial. Okay? Easy. Let's look at this one. This is conjunction. This little inverted V symbol in mathematics means conjunction, or what you know of as ampersand ampersand in CISP360. So this looks kind of awkward. X NAND x, the whole thing NAND, x NAND x, the whole thing. What is that? Well, it's nothing more than x NAND x, x NAND y, sorry, x NAND y, and then negate it. Is that okay? What do you get when you negate x NAND y? After all, the NAND, the N stands for negation, right? So if you negate x NAND y, you get x and y, and it works out. If you're not convinced, once again, use a truth table. Just work out the entire math, and you can see how it works out. So the only one left is OR. And it turns out to be a little bit more cumbersome, but we can get it. We get it done. All right. So let's go through Boolean algebra a little bit here. This is not a class on Boolean algebra, so I will only use it to convince myself and you that the math does work out, but you will not be asked to provide proofs. Okay? All right, so we'll work on this step by step. X or Y, okay? The little V symbol here is representing OR, which you know of as bar bar in CISP360. X or Y. Can we just be kind of extra cumbersome and say, that's the same thing as not X or Y? Sure, double negation cancels out, right? This is the part that gets a little bit cumbersome, interesting. The negation of X or Y can be rewritten as not x and not y. That's the part where it gets a little bit kind of tricky because it's not obvious. So what happens when you look at something like this and you're not 100% convinced that this portion is really the same thing as this portion here? This is, by the way, called De Morgan's law. But what if you're not convinced that De Morgan is right? You guys already have encountered that idea. Use a table, right? So let me do it for you. Okay, this is something that you really should keep in mind, not only for this class, but also for many of your other classes. So what we are doing here, okay, this is going to be the last thing we do in lecture, and then we'll transition to lab in about 5 minutes. Okay, so we got x, we got the negation of x or y. And let me put x, y as individual variables too. So we got one column for x, one column for y, one column for the negation of x or y, and then one more column for the negation of x and the negation of y. Okay. And negation of y. There we go. Okay. So how many combinations do you think we can get out of x and y? They're both being Boolean variables. 4, because x can assume one of 2 values, but when x is one particular value, y can be any of the 2 values. So that's why we got 2 times 2, or 4 possible combinations. So the way I populate this is just my own convention, but you can use your own convention to populate this. Okay, so when x is 0, y is 0, what is the negation of x or y? It's a 1, right? Because x or y itself is going to be a 0. The negation of 0 is a 1. All right, moving on to the next one. In this case, x or y is a 1. The negation of 1 is a 0. Same thing here, and then same thing here as well. Because when x is 1, y is 1, the disjunction or the OR is a 1. The negation of the 1 is a 0. Okay. Now we work out the last column. They're both zeros, okay? The negation of x is 1, the negation of y is 1, 1 and 1 is 1. For all of the other ones, because at least one of the 2 is a 1, that means, with the conjunction, at least one side is a 0, but because it's a conjunction, if at least one side is a 0, the whole thing is a 0. So we put zeros, for the rest of this column. All right, so now that we have worked out the truth table, you can see the column corresponding to the negation of x or y as a whole has exactly the same values as the column for not x and not y. That's the proof. Don't you wish all algebra can be proven with a table like this? You just kind of exercise all the possible combinations of the input. If the 2 expressions give you all the same values regardless of which row, it's done. Okay, yep.
So that's Morgan's law?
That's De Morgan's. That's one part of De Morgan's law. The other way around is all true as well, but we are not using that in this proof. So getting back to here, okay, so now we have this equality established, okay? So when we have that equality established, then we go like, let's see here. What am I talking about? So there's this is applying De Morgan's law. One more time? No, okay, I take it back. If you take this negation on the outside is applied to this conjunction. Is that right? So it's a negation of a conjunction, which is also called NAND. This is what we have been talking about the whole time. So that's why this outermost negation and the conjunction combine to be just a NAND. And that's why we end up with not x, NAND, not y. But wait, we don't have negation. We only got NAND. So we have to re-express the negation of x as x NAND x. We have to re-express the negation of y as y NAND y. So now we are using 3 NAND operators to express OR. Is it cumbersome? Yes. Okay. Is it way more work than it really needs to be? Maybe. But can it be done? Yes. Okay. So even though we only got about, we got 1 minute left, but we already have established with 4 transistors, we can make a single gate called a NAND 2 gate that can, in combination, can implement all of the other logical operations that we have already learned in CISP360. And I think that's pretty significant because from here, we can now move on and talk about how to perform addition, arithmetic addition, using just AND or NOT gates. So are we good so far? All right. So let's go ahead and take a 10-minute break, and then we'll go to the lab. I think it's 4:09. Let me double check. Yep, it's CMC 4:09. So I'll see all of you at noon time at, in room 4:09. You held on to it.
Yeah, when I look at that, I noticed that the class on that was actually different from the one I have here.